All right, so today we're going to have Jungseock Joo talk about understanding gender and racial media biases in computer vision. Jungseock Joo is an assistant professor in communication at UCLA. His research primarily focuses on understanding multimodal human communication with computer vision and machine learning. His research employs various types of large-scale multimodal media data, such as TV news or online social media, and examines how multimodal cues in this domain relate to public opinions and real-world events. His research has been supported by the NSF, Hellman Foundation, Samsung, and the UCLA Faculty Career Development Award. He received a PhD in computer science from UCLA, a master's in computer science from Columbia University, and a BS in computer science and engineering from Seoul National University. Prior to coming to UCLA, he was a research scientist at Facebook in 2016, before joining UCLA in 2016. And with that, let's hand it over to Jungseock.
Yep, thank you very much for the intro. So that's my brief bio. So first of all, thank you for having me in this virtual talk. I know it's a little old, but I have given talks and also teaching online in Zoom and other types of video conferencing. And then so far it's kind of pretty okay, you know. It's convenient. So it's good that we have this kind of a technology that supports, teaching and also working, collaboration and communication, many things. So, I'm directing Computational Media Lab at UCLA, and the common research areas are basically to apply computer vision and deep learning, machine learning, and other types of computational methods for data science and also computational social science research. And in particular, my background is computer vision, meaning I specialize in analyzing visual data. Right. And then specifically human communication, as in face-to-face communication, but also media, social media and mass media. Those media platforms provide us with a lot of data, multimodal data, so not just text, audio and video, and enormous amount of those kind of multimodal data gave us a lot of opportunities to discover and learn and gain insight about how humans communicate through these different types of technology. And then my main research goal has been to develop and apply advanced computational means to automatically analyze those kinds of multimodal data so we can scale up existing sort of traditional manual and qualitative analysis on those audiovisual data. So today's talk will be about fairness in computer vision. So fairness, there's I think pretty big literature and very active research area going on in many disciplines, including computer science and also social science, where researchers focus on trying to measure and quantify biases encoded in AI systems or classifiers or datasets. And then also people are trying to mitigate those existing biases. And because these issues of fairness and model transparency and accountability, these are important issues because we are getting to see more and more AI driven products around us. A lot of them, software that we're using, and also personal devices equipped with, AI functionalities they can understand human comment and intellect with humans. So there are a lot of issues. Another example might be personalization in media and personalized ad. So many types of services we're getting from online and offline are assisted by some kinds of AI and machine learning functionalities. So it is vital to ensure that those methods that we're using are transparent and fair, in the sense they don't create another layer of discrimination against some populations, some subpopulations in our society. So the this illustration is pretty simple, and then so one of my core interests and main concern in the area of AI fairness, and also in general through my research topic and themes, the important question that I want to ask is so how these elements in fairness or in artificial intelligence in general sort of intellect with each other. So when I'm saying elements in AI, that includes obviously data and model and society and human, our thinking. So those are related, although we often only focus on one aspect at a time, which is good approach when you want to isolate the problem and then understand it better by going deeper into each domain. That's important approach. But there are obviously a lot of intellections and then kind of causal roots behind this problem. So for example, a lot of times what we discover as a model biases, the bias decisions made by classifiers, for example, those are caused by the fact that underlying data, which was used to train those classifiers, were actually biased, right? But the reason that those data was biased was because the data was collected from online web search, where biased or skewed population of people participate in contributing the data to the platforms like Google or Facebook or Amazon, right? Any kinds of platforms which offer large scale data that can be used to train the models, right? So that's biased. And another source of bias is actually human bias. So it's not necessarily the issue of unbalanced population in the platforms, but oftentimes these machine learning classifiers require human supervision, meaning annotations, right? So we often use the original raw data and also human annotation or human judgment, human ratings in the form of reviews or labels. So those things could also kind of be biased, because that's the bias and stereotypes and our cognitive preference that we all have. So eventually, so what I want to verify through these studies that I'm gonna show you today is to show what are the connections and intellection between these elements in AI fairness. And it is important to understand those intellection, because that will help us identify the core problem and then fix the problem. But at its core, so I think this is essentially a measurement problem. So measurement of bias is the first step. So if you can measure the bias, then you can mitigate. So in other words, if you can't measure, then you can't fix it. So if you have, for example, if you have a way to measure and quantify the amount of bias in model training, then an easy way to fix the bias is to incorporate that bias as another loss function. When you're training your neural net, it doesn't matter. The network was trained for classifying text data or visual data or audio data. So as long as you have an objective way to measure the amount of bias, or you have a specific terms or variables that you want to decorrelate, and you have a systematic way to observe the biases or constraint that you can enforce in model training, then fixing it is relatively doable. But the issue is how do you actually measure it objectively? So that's the core question in many cases. So I will mainly talk about two of my recent projects. So one focusing on developing a new data set, which can help the biases coming from unbalanced data. And the second thing is to use a recent method in computer vision literature that can be used to manipulate image content by generative models. And then we're going to use that approach to generate counterfactual examples to measure counterfactual fairness in existing models. And these models are black box models, so we don't know how it is structured or how it was trained. But there could be some frameworks that we can develop to examine the hidden biases in those black box models. So those are two things, and then I will just briefly, very briefly, talk about the another source of bias, which is a human bias. And these are kind of ongoing projects, so feel free to ask any questions and give me any feedback during the talk and also after the talk. Okay, so first I want to give you a little bit more information about why I was into this area of AI fairness. So so this is again what I'm doing. I develop a lot of machine learning tools to analyze human social behavior using multimodal data from social media and mass media. And then I'm using a lot of tools. We sometimes develop the tools and classifiers from our lab, but we often just use the off-the-shelf tools because it's easy. And a lot of times actually they are pretty reliable. So this is actually a good thing in machine learning in general, especially in computer vision. So when I was doing computer vision PhD, several years ago, there were not that many reliable tools that I could use. So I had to build everything from scratch and then validate it and then and deploy it. So it was a lot of work. But nowadays there are so many tools just available. So a lot of social scientists are actually starting to use those classifiers, neural networks, for their research. But the quality or the validity of those tools are largely unverified. And that is a problem because in a situation like this, which I'm providing as a reference, so this is one of the example project that we're doing at UCLA, where we're trying to use Twitter data, Twitter text and images to monitor and track global protest activities in different countries. And actually, my co-author gave a talk at USC, I think last year. So probably some of you have watched this presentation. But anyway, so what we want to do was to use a neural network, CNN, to classify the protest images from Twitter images. So we have a pipeline of a Twitter geolocated Twitter images. And then we first detect whether there are any protesters in those images. And then we classify how violent they are. and then who they are. So when I say who they are, we don't identify individuals, but then we want to classify their race, gender, and age. So we know, so we can understand what are the demographic characteristics of the protesters in different countries, and what are the interactions between that characteristics and then the subsequent progress in protest event. So when we were doing this analysis, we trained some face models because we wanted to infer those demographic attributes from face and gender. Gender from face is usually it's pretty reliable. Gender classification from face images, it's not really difficult. But what happened was, so we trained a model from existing public model, public data set. So there are a couple large scale public computer vision data set that can be used to train a model for face gender classification. There are many of them. So we train a model from this data set and then apply that to event data that we have. And then what we found was in women's march event, so we found more males than females in our data set, which is not true, right? So women's march was attended a lot more by women than men. And if you see sample photograph like this, it's very clear. But the classifier SOP, there are more men than women. So accuracy would be 60 or 70%. So we manually validate the gender for some subset, and then accuracy is very low. So 60 to 70% accuracy for gender classification means it doesn't work. And it's very surprising because if we read the papers, recent papers of gender classification, so actually people no longer works on gender classification from face. It's considered solved problem, a long time ago. Actually, if you look at the accuracy, it's 95% or 97%. So it's largely considered as a kind of solved problem, but it isn't. So that was a problem. So what happened is this: why we think certain problems in computer vision and more broadly machine learning, why we think we solved the problem, but we didn't, was in this case was because we have separate modules in a pipeline of analysis. So if you want to classify gender of people in the photographs, the first thing that you have to do is you have to detect any face, meaning localize the instances of faces. And then alignment, meaning you want to detect the fiduciary points, landmark points, such as the corner of your eyes or nose, so you can transform these rotated images to the canonical form to improve the accuracy. And then do final classification, whether the person is a male or female, right? So that's the several steps involved in this gender classification. The problem is when people train this model, we use different data set. So each module is typically trained by different data set, and their distributions are very different. So for example, this is common recent data set that people commonly use to test or train and test face detector. And because the core problem of detection is to find that faces in occlusion and also rotated. So you have a lot of difficult images because easy faces like frontal looking, clean facial images were already proven to be easy to detect like 20 years ago. So it doesn't make sense to just work on the same data set. So they made a new data set, right, for train a detector, right? But for classifier, this is very popular and very recent data set that people use to train facial attributes such as gender, age, or expression, emotion, or hairstyles. And you can easily tell the difference between two data sets, right? So one is very difficult, the other is very easy, right? But this distribution is different. So what happens is we have to train the module separately using different data set. But once you construct this whole pipeline, and then you're gonna deploy it. And when I start to use it, and then pass on images, and that's difficult images. So let's say, rotated images, right? Rotated faces. And then that'll pass the first two steps without a problem, detection and alignment. But then when it reaches the last step, which is the classification, then that module, that classifier, gender classifier, has never seen examples like that when it was trained. So it doesn't work, right? But the problem is that we didn't know, no one knew, because there's no data set that could be used to evaluate the whole pipeline. So wider face, this data set was used to evaluate this first two, detection and alignment. And actual alignment is probably a different data set. They're both using a difficult data set. The classifier was evaluated on a separate data set. So if you evaluate detector, alignment, classifier separately, then everything will yield very high accuracy, near 100%. But when you put them together, it doesn't work. So what you have to do is pretty easy. You need to make a data set that can be used to train and evaluate this whole process, not just subset of these modules. And that's what we did, right? So we're actually surprised that we couldn't find such a data set that is challenging and then have a lot of metadata labels for attributes and alignment and detector. But we couldn't find any of this. And probably because we were not aware of the fact that this actually doesn't work in many cases. So probably many of you are familiar with this gender shade study. And actually, I thought this talk would be short. Probably I thought I could have done like in 30 minutes, but I only spent 20 minutes, so I'm gonna be quick. So this study is a very famous study in the literature of fairness in computer vision. And what they did essentially was to test the accuracy disparities of existing commercial computer vision classifiers developed from Microsoft Face++, many companies. So those companies provide pre-trained gender classifier from facial images. And then the researchers in this study wanted to verify the classifiers will make equally good classification on different subpopulations, white male or black female. And what they found was black female, dark-skinned females, the classifier, made the worst accuracy on the set of the dark-skinned female compared to light-skinned males. So light skin means white, and dark skin means black, right? So but they use skin color rather than race, right? So what they're saying is the classifier overall is very accurate, but it doesn't work well on some subpopulations. The black population, that was the problem that they discovered. So this is a good finding and actually suggested many important directions that these communities can be headed. but there are certain limitations. I will just quickly go through some of them. So in order to measure the biases in existing models, then you need a better data set. Better data set means you need balanced data set to measure how balanced the other data sets or classifiers are. But their data set wasn't really balanced. Well, it was balanced in terms of number, but the quality and then the other types of presentations show actually the samples were not actually balanced. And then another issue is this. So they use the facial images of politicians in 6 different countries, 3 from Europe and 3 from Africa. And that means, what they found could have been actually attributed to the cultural variation rather than the variation in face. So another issue here is actually the politicians' face are not good samples to use in this study in general, because they're not random samples. They're not representative samples that you want to use to model the facial appearance of the whole population, because they're very specific set of people in the society, and then they tend to have competent looking faces. There's a huge literature in social science and psychology showing that actually people may choose politicians by their looks. And their theory is because we want to infer the personalities and personal traits and their qualification quickly. So we tend to use their facial appearance. So that means their facial appearance itself is actually biased. And moreover, there are actually many research saying the female political leaders tend to have masculine features. And again, because of voters, the public prefer stronger leaders. And stronger in this context means more masculine. Right? So short hair, for example, is a masculine feature compared to long hair. So a lot of high-profile female politicians, they were very short haircut. And not even for high-profile politicians. Then several research actually show that the correlation, association between the masculinity of facial appearance of female politicians and their electoral success. So overall, this is not good set, good samples that you can actually use to validate or measure the biases in other data sets or models.
Excuse me, as a short-haired woman, can I just pipe in for a second and tell you there's another bias could be creeping in here which you don't realize because you probably never had really long hair. The time it takes to take care of long hair is enormous and interferes with your job, other responsibilities. So there could be, nothing to do with power, could be, trying to generalize from too little evidence, but maybe all to do with how busy high-profile women are.
Oh yeah, that's actually a very good point. I never had too long hair in my life, so I didn't realize that. That might be something that people also infer. Like when you see politicians, women politicians who have a long hair and then wear heavy makeup, then people may think, well, these politicians they spend a lot of time just decorating themselves and not spending enough time to take care of the important things that they have to. So that might be the reason that they think,
By the way, watching Trump's press secretary, I forget her name, McKeon, something. Not only that, she has long hair, but not only that, either her hair is really straight or either it's kind of wavy. Both of those things, straightening the hair or making it curls, takes at least an hour, maybe even more.
Yeah.
So I can deduce from that she spends inordinate amount of time on her hair, doing prettifying herself for the cameras.
Right. Yeah. So actually, that's also a very interesting point. And actually, so my colleague at UCLA, my department, Carrie Johnson, so she has done this analysis. And then what she says is actually there's a difference between Democrat female and Republican female politicians. So what she found was Republican females are prettier and kind of tend to have a longer hair and then groom better, and that might be because that's the expectation from voters, Republican supporters compared to Democrat supporters. So there could be some party differences as well. So I think overall, and there are a lot of issues, and then actually, you may be surprised that there are a ton of papers in social science just focusing on the facial appearance and or visual display of politicians in mass media and social media. So the bottom line is we don't want to use this data set to test your general computer vision models, because your computer vision models are not trained to just handle this politician faces. So this is not a good set. And there are some other issues, but I'm gonna skip that. So, so what we wanted to do was to make a much larger scale data set, and then which can also generalize better, and then can be used not only to evaluate existing model, but also to train a new model. And again, the part of motivation for me was I actually needed to have reliable face classifiers that I can use to classify gender and race and age. So I couldn't find any. So so I wanted to have some big data set that I can train a reliable model. So there are a couple of studies in this topic arguing that actually we should not use race as a basis to measure and quantify representativeness of the samples, data set sample, data sample. But we use races because the skin color is not a good indicator to measure a diversity in race, because there are dark-skinned white people and also light-skinned black people, and there's no easy way to objectively measure the skin color from photographs. And then we also needed many different racial categories. So we use races. We specifically categorized and labeled races. So we use so our source for our data set was Yahoo Flickr Creative Commons data set. So this is the data set that Flickr published. And this data set has a lot of image and video data, and then users clear the permission to use this data for any purposes. So we use those data set, and then we first do some random samples and then label their races, and then we quickly found we had enough number of white faces. So because we wanted to balance the race and gender in our data set, so we stopped collecting white faces after that point, but just increased the other races, so that we overall have 100,000 facial images, and then we annotate their gender, age, and races by multiple people using Mechanical Turk. So these are some random samples from our data set. We named the FairFace, the top left, and then compare to other data sets of a facial attribute. And you can easily tell, we have a much more diverse face orientation and race composition, also balanced gender in our data set. And this is a comparison of the racial composition among different data sets. And basically all the other data sets are white focused. I'm sorry? I'm sorry? Could you say it again?
I'm sorry, nothing.
Okay, yeah.
But I have a question. This is
Sure.
Christina again. So you're saying it has balanced representation, but what if you have basically like population? I mean, it obviously doesn't reflect the prevalence of the races within the United States, for example. Is there a reason to go for like balance basically composition between classes versus having it reflect the prevalence?
Right. Yeah, I think that's a good question. So the first priority in our design was to make sure that we have a minimum number of faces for each racial category. So so we had about I think 10,000 for each racial category. So like United States and then other countries, they do have more white faces. But once you have about 10,000 faces, then we found actually the classifier accuracy was reliable. And then adding more samples on that particular category wasn't as helpful as adding more samples in other categories which do not have enough samples. So it's of course possible that we can add more faces from our data set. And then we'll have unbalanced data composition. Well, I think that's fine, but what we wanted to show and then what we wanted to do was to make sure for every category of races, we have at least 10,000 faces.
Thank you, Jungseock. One point I just want to point out, which is that I'm noticing we're starting to get short on time. So let's hold off on questions until the end, or if you can talk to him
Sure.
in your own time. Thank you.
Right. So so I will be quicker. So we did validation. So we compared our model, and we first fixed the model architecture and then train a model from our data set and compare that with the other models from other data set. And then our data set was in general better, even when tested on their data set. And then very important issue is how well does it generalize? Because the reason that the community couldn't find this problem earlier was because the practice of evaluation was it still is, that we collect some data set and randomly split this into train and validation and test, and then train a model on the same distribution and test on the same distribution. So it doesn't really tell us how well it generalized. So what we did was to collect another set of data set, completely independent from our data set, and measure the accuracy. And then what we found was the overall, our model was able to achieve the best accuracy, but also the lowest standard deviation in terms of accuracy across different racial and also gender groups, meaning it's reliable and accuracy disparities is the lowest, meaning it's consistent. That's what it is. So this is a visualization using Tisney, and then and what we found was, of course, our data set, because we have so many different races, and the boundary between races may not be so clear. And of course, because there are people in mixed races, and sometimes annotators find some faces hard to classify into one racial category. But I think this is a good thing to make sure the data set covers diverse sample space compared to other data set which focus on just kind of stereotypical looking face samples. And then we also found the distance between samples was also higher than the other data set, meaning our data set, again, covered the larger space of facial appearance, meaning it's more diverse. So we use this data set to train our model, but another thing that we could do is to use this model to benchmark the other classifier, existing classifiers. So we tested the classifiers for face, the gender classifier, which was originally tested in the gender shade study. What we found was the accuracy disparity was lower than what was reported before. But then maybe because these companies made some changes after the initial report, saying that their models were biased. But it may be also because we used more balanced samples, which may be closer to the training data, which was originally used to train their models. But what we also found was the gender classification or race classification was kind of okay, but the detection was problematic. So we said, there are different modules in the pipeline, and then detector and classifier are separate modules and evaluate separately. But what we found actually, some classifier like Microsoft had a trouble detecting female faces compared to male. Although once they detected those faces, they were able to correctly and consistently classify the gender. So again, the message here is, again, we need to evaluate each stage in a pipeline separately and also jointly. And then this data set was made for that purpose. So that was one study. The second thing, I can probably go through this quickly. So that was so that study was to develop a data set that can be used to evaluate the model bias and data set bias. But another issue is, so when you are given a model, and then that model is biased, the model fails. But the question is, why is it failing? So where does the bias decision coming from is another question. Because the whole data set, if you look at whole images, there are a lot of objects and attributes and many different visual features. So what exactly triggered the bias decisions of the classifier is an important question. Because it might be gender, but it might be background objects. So we wanted to identify the inherent and the core variables that cause the bias in the model outcomes. So this is known as a counterfactual fairness in the literature. And then the way that we want to measure the counterfactual bias is to generate new samples, synthesize samples, to measure what the classifier would have output if we only changed gender, for example, and leaving everything else the same, right? So we don't want to change anything but face is what we wanted to do. So there are many methods in computer vision and also other domains of machine learning where people use generative models to manipulate certain attributes only from given inputs. So this is the process that we're doing. So we first detect the face and then segment the skin region. And then we are only changing the femininity or masculinity of a face, but we're not changing everything else. So then we're gonna make a series of the identical images. They're identical except their facial content. And among the facial content, we're only controlling the amount of femininity or masculinity. And what you're seeing on the right side is some sample examples. So what we're gonna do is we're gonna use these samples, these 3 images, these 3. Yeah. I don't know if you can see my cursor. And then submit this to the classifier and then measure how sensitive your classifier output will be against these 3 images. So if your classifier is biased against gender or against female, then means as you increase femininity or decrease masculinity, your output will be also expected to be affected by the amount that you are manipulating, is the idea. So there are some similar work in the literature, which actually published last year. So this model is very similar, but one core difference is so they use GAN, which is just trying to reconstruct, to generate the realistically looking faces, but the gender was not used in training that model, but discovered later. And then the limitation of this method is the gender cannot be separated from other attributes, like facial expression or hair or glasses or other types of variables. We want to separate those variables and then just want to examine the gender cues and how gender cues control the classifier output. So we use the other method. So and there are some examples. So we collected some example from Google Web Search. So we had a bunch of profession-related keywords. Doctors, scientists, teachers, nurse, many things, and then manipulate their masculinity, and then use classifier from Google, IBM, Amazon, and also Clarify. So those are the companies which offer pre-trained label visual concept classifier. And then what you're seeing here is essentially, so as masculinity increased, the model give higher confidence on concepts like doctors, surgeon, physician, and also engineers, scientists, building anything. Whereas they higher the models assign higher confidence for more feminine faces for concepts like nurse, teachers, kind of socializing, those kind of things. And those are the list of concepts which were which shown the significant correlation between the degree of our manipulation and then changes in their output. And I think these are all male, and I have a separate table for female, but I don't have it here. But you can think there are nurse and then other types of occupations, primarily held by women, and this is a very consistent effect across different APIs. Although some companies did better than the others controlling this effect. So this is probably because they use skewed data set when they were training their models. So we also measure the skewed representation in the data that we were able to scrape from Google Web Search. And again, nurse, hairstylist, those are occupations which show more women in image search. And pest control worker, handyman, those are top occupations which return images of men workers. So interesting question that we could ask was to compare how much this skewed representation in media could have impacted the AI biases And then that's, we haven't done it yet, but probably going forward, that's going to be an important question because we want to study, again, the chain of biases, how this biases propagated and then also amplified over the course of a chain of a development, and then also collecting data set and also deployment. So, so one last thing, just one slide for our current work is, so there's another layer of bias, which is human bias, annotator biases. So all the other studies in the literature, including mine, assume the human labels are gold standard. So when we measure biases or when we want to decorrelate variables, so we take the human labels as gold standard and absolutely correct references. So we can decorrelate or adding a loss function that will penalize, when your classifier is using gender-related cues. But this may not be a valid assumption in some cases, like emotion annotations. So emotion and classifier from facial appearance, for example, would require human judgment and ratings about emotions and perceived emotion from another people's faces. And then people show biased judgment there. So people may tend to perceive the women faces happier than male faces, even when those are just neutral faces, or opposite direction. So again, there are many research showing this interaction between race, gender, and age, and then the perception of emotions. So we're pretty early stage on this project, but the important thing is the even human annotations may introduce another layer of bias to the the model bias and also data set bias, which is important to address. So overall, so the messages and the lesson that I learned personally is a lot of times, so the way that we evaluate this machine learning or AI models may not be sufficient. Especially when you are deploying these models outside of the context of your current research, it may not work. It may fail very bad. And that is, limitation, but not surprising because again, the way that we evaluate, the model in machine learning papers is, again, you have one data set, the same data set, and then random split train and test into split train and test, and then evaluate the same model from the same distribution and then apply that to the same distribution. So that's not good. And then of course there have been separate research problems of domain adaptation, which actually essentially test the generalizability of classifiers and models, but that hasn't been adopted as the normative way of evaluation. But it should be, because otherwise we don't know how robust this model will be when people are using in different domains. So that is dangerous, especially these AI products are getting deployed in many parts of our society and human lives. And for computational social scientists and also data scientists, it is important, very critical to make sure those tools are readily available and also robust and reliable, and independent of those issues like a data set bias and model biases. Because typically social scientists do not have a means or resources to measure those biases or mitigate it. They're not computer scientists, right? They are just using these tools as is. So the community in machine learning and computer science will probably need to spend more effort to deliver better product, which can also enhance the impact of this machine learning models outside of their community. I think, yeah, that's it. Spend more time than I thought before. So I am happy to take any questions.
Yeah, thank you, everyone. Since we have just a few minutes left, it looks like Christina raised her hand. I would like to let you have a chance to speak.
Okay, hi, thanks. Interesting talk. I had one question. So for skill profession representation, why to become fair, why don't algorithms just blank out the faces and just pick up the cues from the clothes and the props that people are having, you know? What would that be like, you know, a fair training algorithm?
So, I mean, yeah, if the algorithms, the models just use the clothing and other cues, it may be fairer than the current way. So the current way is just to take the whole image as an input. And then they're gonna use whatever cues that they can find in images. And then what happens is, you know, the gender cue was found as very informative cues in professional classification. So that's what we are saying is biased, because gender has no you know, causal relationship to you know, profession. Although it's a
except that there's Bayesian, yeah, priors for being men, being women is probably higher for online images, yeah.
Right. Yeah.
But,
so,
but maybe that's what you should be comparing to, you know, the unbiased algorithm, the one that takes the faces, completely blurs out the face and just. Right.
Yeah, so yeah, completely blur face. And I think there was some paper doing that, like actually just excluding that the regional faces. What we wanted to do was to still have faces, and then just control the masculinity, so that the classifier still use faces, still see the face, and then probably just still the same gender, but you just change a little bit of masculinity, so that you can test the whether the model is actually biased or not. So because like if you just blur the face, like, you know, no face in this region, it's not person. So the correct answer is it's not doctor, or it's not nurse, or it's not anything, because there's no content. And then our assumption here is so we want to test black box models, like from you know, those companies. So we don't have a control to change the parameters anymore. We just want to validate this final product. Without assumption that we actually can change anything. So that we wanted to deliver still valid input, still there's person, and then just change the masculinity or femininity, and then see whether that changed their output. And if so, then we consider that as biased.
All right, I have more questions, but I guess I'll ask on my one-on-one meeting with you.
Yeah.
Well, thank you very much.
Yeah, thank you to Jungseock and Christina. Those were very good questions. I just want to point out that it's after 11:30, so or 1:30. So it seems that we're out of time, and to give people a chance to go to their next meetings. I just want to say thank you, Jungseock, and if you're here, we would clap for you.
Yeah, and also let's clap, because in Zoom meetings you don't get the appreciative audience.
Yeah, thank you very much. Yeah.
Thank you.
Yeah.
Thanks.
Thank you. All right, we'll see you soon. All right, I'll stop recording and end this meeting.
Sure. Yeah.